In this video, we'll be talking about LRCs, or longitudinal redundancy checks. LRCs basically say that instead of adding a single parity bit to each byte of data we've got, what we do is we have a whole chunk of data, there might be hundreds or thousands of bytes there, and we compute a checksum based on that data. And we append that checksum right at the very end. So that checksum might be a 1 byte or 2 byte checksum or something like that. Something quite small, and hence if we're dealing with a decent chunk of data, the overhead for appending this LRC is actually quite small compared to the overhead of appending parity. What we do, we compute the checksum at the sender, we compute the checksum at the receiver, and we make sure they match. If they don't match, something's gone wrong, either with the checksum or with the data somewhere that there's been corruption in the data. So compared to parity, we've got less transmission overhead, which is really good. It's also more reliable in detecting errors. So we can detect not just 1-bit errors, but multiple bit errors. And we can detect if characters are missed or they're being dropped in some way, shape or form. So we've got a couple of different algorithms. And the first one we'll look at very briefly is the ISO 1155 standard. And basically in this standard, what we're doing is for each byte that we've got in our data, what we do is we add it to our LRC value and we AND it with FF. And basically what that will do is chop off anything above our 1 byte that we've got there. So if you AND something with a 0, which is whatever's above FF, the result is 0. So it will chop off anything greater than 255. And once we get to the end of there, we XOR it with FF, which essentially inverts all those bits, and we add 1 to it. Now, once we've done that, we've got our result there. Now, here's some examples of how it plays out in practice. So you look, if we've got a string that we're going to send, which is A, B, C, D, $. So we start with A, which in hex, if you look in an ASCII table, is 41. And our LRC result at that stage is 41 because we've added A to our LRC. Then we add B to it. So we add 42 in hex to that, which gives us 83. We add C to it, it gives us C6. Then we add D to it, which is 44 in hex. And when we do that, we get 0x10A. Now, what we want to do is chop off anything above the 255 or above the FF in hex, which gives us 0x0A. Then we add the $sign to it, and we keep on going as many bits as we had. But that's all we've got for the moment. We get all those, we work out what they are in binary, we flip them and add 1 to it, and that's our LRC checksum result. So we can do that at the sender side, and then at the receiver side, we compare the two and make sure they match. Here's another LRC algorithm. This one I've seen a lot more. It's quite a popular one. It's used by things like GPS, electrical meter reading, some smart cards and things like that. And basically what you do in this one is you XOR your LRC, whatever particular value you've got there, with your current byte that you're looking at. So when you XOR something with 1, it flips a particular bit. If you XOR something with 0, it leaves as it was. And so you go through and just XOR each one. So super simple to implement. The other one was pretty simple as well. And you just go through and check all of those. So here's how it looks like. Is it most easy to see these in binary? So you see the first one ends up as 41 in hex or in binary. Then we XOR it with 42, and when we XOR it with 42, anything where we've got a 1 XORed with 1, it changes to a 0. Anything when we've got a 1 XORed with 0 changes to a 1. And so that's what we've got there, and we can step through each of those steps. And at the end what we've got is 0x20, which is our LRC at the end. So important to note, when we're implementing an LRC, make sure it's the same LRC on the sender and the receiver because they'll give you different results.